Welcome back to Artificial Intelligence and Machine Learning with Typical Monk, Class 2, How Machines Learn. Last class we discovered the one idea behind all of modern artificial intelligence, that instead of a human writing every rule, the machine learns the rules from data. Today, we open up that word, learn, and see exactly what is happening inside. And I promise you this, there is no magic in it, and there is no heavy mathematics either, just one beautifully simple loop, repeated a great many times. Here is that loop in a single breath. The machine makes a guess, it measures how wrong the guess was, and it adjusts itself just slightly to be a little less wrong next time. That is it. Predict, measure the error, adjust, over and over, thousands or millions of times until the guesses become genuinely good. Every model you have ever heard of, from a spam filter to ChatGPT, learns by some version of this exact loop. Over this class, we will walk through it, piece by piece. The data a model learns from, the adjustable knobs inside it, how it measures its mistakes, how it rolls downhill toward the right answer, and the traps to avoid along the way. In Hindi and English together, one idea at a time. Now is the map of today's class. 6 ideas that turn the machine learns from a mystery into something you can actually picture. First, the learning setup, the 3 things every model needs. Second, training data, features and labels, the examples a model studies. Third, the model itself, a box full of adjustable knobs. Fourth, error, and the idea of rolling downhill to reduce it. Fifth, training versus testing, and the twin traps of overfitting and underfitting. And sixth, the 3 great styles of learning, one idea at a time. Before a machine can learn anything, 3 things have to be in place. Miss any one of them, and there is no learning at all, so let us name them clearly. The first is data, a pile of examples, and for today, imagine each example comes with its correct answer already attached. This is the experience the machine will learn from. Without examples, there is simply nothing to learn. The second is a model, and for now, picture it as a box full of adjustable knobs. At the very start, it knows nothing, so its guesses are pure nonsense. But those knobs can be turned, and that is the whole point. A model is something that can be changed. And the third is feedback, a way to tell the model how wrong each guess was, so it knows which way to turn its knobs. The model guesses, the feedback corrects, the model adjusts, and the cycle repeats round and round. So the takeaway, learning needs 3 things together: data to learn from, a model that can be adjusted, and feedback that guides the adjustments. Hold these 3 in mind, because everything else today is just a closer look at how they work together. Let us start with the fuel of the whole process, the training data. Its quality decides everything. A model can only ever be as good as the examples you feed it, and that data has a very particular shape. Every example splits into 2 parts. On one side are the features, the clues, the facts you know about each case. For a house, that might be its size in square feet and its number of rooms. On the other side is the label, the answer you are trying to predict. For that house, the label is its price. No lineup, many such examples. This house with these features sold for this price, that house for that price, and so on. Row after row. Each row is one complete lesson. Here are the clues, and here is the right answer they led to. The model reads through all of these rows and slowly works out how the features connect to the label, how size and rooms relate to price. The learned connection is exactly what lets it predict the price of a brand new house it has never seen. So the takeaway, training data pairs features, the clues with the label, the answer, and the model's whole job is to learn the pattern that links one to the other. We keep calling the model a box of knobs, so let us make that picture precise, because it is the truest way to understand what a model really is. Inside the model sits a collection of numbers called weights or parameters, and the knob is the perfect way to imagine each one. Every knob controls how strongly one clue pushes on the final answer, how much the size of a house matters versus the number of rooms, and so on. At the very beginning, before any learning, all these knobs are set to random positions. So the model's first predictions are hopeless, wild, meaningless guesses. that is completely expected. An untrained model is supposed to be bad. Learning is nothing more than the slow, careful turning of these knobs into better and better positions. And here's the scale that makes modern artificial intelligence so powerful. A simple model might have just a handful of knobs, but the large ones, the models behind ChatGPT, have millions, even billions of them. That is where their astonishing ability comes from. Now the takeaway, a model is a set of adjustable knobs, its weights, that begin at random, and learning is the patient process of turning every one of them toward the right value. Now, we can watch a single step of learning happen. It begins with the model making a guess, and then being told precisely how wrong that guess was. We take one example and feed its features into the model, say, a new house of 1500 square feet. With its knobs at their current settings, the model does its calculation and produces a prediction, its best guess at the price. Then we compare that guess against the real answer we already know for this example. Suppose the model guessed 400,000, but the house actually sold for 310,000. The two do not match, and that gap is the whole point. That gap has a name, the error or the loss. Here it is 90,000, a simple, honest number that says exactly how far off the model was. A big error means a bad guess. A small error means a good one. This single number is what the model is desperate to shrink. So the takeaway, the model predicts, we measure the error, how far the guess is from the truth, and that error becomes a signal that drives all the learning that follows. So the model has an error, and it wants that error to be small. But how does it know which way to turn its knobs? This is the very heart of machine learning, and there is a wonderful picture for it. Imagine a curved landscape, like a valley. Every possible setting of the knobs is a spot on this landscape, and the height at each spot is the error for those settings. High up means a big error. Down in the valley floor means a small one. Our model, with its random starting knobs, begins somewhere high up on the slope. Learning is simply rolling downhill. The model figures out which direction is downward, which small turn of the knobs would reduce the error, and it takes one little step that way. Then it looks again and takes another step down and another. Step by step it descends until it reaches the bottom of the valley, the point of lowest error, where its predictions are as good as they can get. This downhill stepping has a real name you will hear often, gradient descent. But the picture is all you truly need, a ball patiently rolling to the bottom. So the takeaway, learning is rolling downhill. Each step nudges the knobs to lower the error until the model settles at the bottom at its best possible fit. Now, a crucial idea that separates a model that truly learned from one that merely cheated. It comes down to how we split our data. Take all the data you have and divide it into two parts. The larger part, usually around 80%, is the training set. This, and only this, is what the model is allowed to learn from. This is its textbook, its practice problems. The smaller part, the remaining 20% or so, is the test set, and it is locked away in a drawer while the model trains. The model never sees it during learning. It is being saved for one purpose only. Then, after training, we bring out that test set, data the model has never laid eyes on, and we check how well it predicts. Now, Mamas is the real exam. If it does well here, on genuinely unseen data, then it has learned something real, something that generalizes beyond the exact examples it studied. So the takeaway, split your data. Let the model learn on the training set, then prove itself on the unseen test set. Doing well on data it has never seen is the only honest proof that a model has actually learned. That train and test split exists to catch two opposite failures, the twin traps that every machine learning practitioner must balance. Let us see all three cases side by side. On the left is underfitting. Here the model is too simple to capture the real pattern, like drawing a single straight line through data that clearly curves. It is lazy, it misses what is plainly there, and it predicts poorly on everything, training data and test data alike. In the middle is the goal, a good fit. The model is just complex enough to follow the true shape of the data, the real underlying pattern, without getting distracted by the little random wobbles. This is the model that will predict new cases well. And on the right is overfitting, the sneakier trap. Here, The model is too complex, so instead of learning the pattern, it memorizes every single training point, wiggling wildly to pass through each one. It scores perfectly on the training data, and then falls apart on the test set, exactly like a student who memorizes last year's exam paper word for word, and is lost the moment the real questions come out differently. It learned the noise instead of the signal. So the takeaway, too simple, and the model underfits, too complex, and it memorizes the noise, and the whole art of machine learning is finding the balance in the middle. Finally, everything we have described today is one flavor of learning, but there are three great families, and it helps to know where each one fits. The first, and the one we have been describing all class, is supervised learning. Here every example comes with its correct label, the answer is supplied, and the model learns to reproduce it. It is by far the most common style in practice, powering everything from spam filters to price prediction. The second is unsupervised learning, where the data has no labels at all. Here, the model is not told any answers. Instead, it hunts for hidden structure on its own, grouping similar customers together, say, or spotting unusual patterns. It finds order that no one pointed out in advance. And the third is reinforcement learning, where the model learns by trial and error, guided by rewards and penalties, much like training a pet or mastering a game. It tries an action, sees whether it was rewarded or punished, and gradually learns the behavior that wins. This is how machines learn to beat the world's best at chess and Go. So the takeaway, there are three great styles of learning: supervised, unsupervised, and reinforcement, and nearly every artificial intelligence system you will meet is built on one of them. Let us gather the whole class in one breath so it locks into memory. Learning needs three things together: data, a model, and feedback. Training data pairs, features, the clues, with labels, the answers. A model is a set of adjustable knobs, its weights, that start out random. Learning is one loop: predict, measure the error, and nudge the knobs downhill to reduce it. Fit the data into train and test, and balance carefully between underfitting and overfitting. And there are three great styles: supervised, unsupervised, and reinforcement learning. Next class, why data is everything, the fuel behind every model. One idea at a time. Predict, measure, adjust. It is worth pausing on how simple the real secret turned out to be. A machine does not learn the way we imagine. There is no sudden understanding, no spark of insight. There is only a guess, a measurement of how wrong that guess was, and a tiny adjustment in the right direction. Repeated patiently an enormous number of times. Turn the knobs a little, roll a little further downhill, and check again. Do that a million times over good data, and wild, random guesses slowly harden into real, reliable skill. Everything else in this field, the neural networks, the large language models, the tools with famous names, is built on top of this one humble loop. Master this idea, and you hold the key to all of it. From here, we put it to work. Next class, why data is everything. The fuel behind every model. One idea at a time. This is how machines learn.